Good evening. Today we're going to be talking about relations, equations with two variables, x and y, and how to graph, kind of the basics of graphing. The first thing I want you to know is that we have this definition of something called a relation. This is one of the more important concepts in math because a relation is any set of ordered pairs. Some examples of relations would be any sort of dots on a graph. I just kind of put some dots in random places. It could be lines, it could be squiggles, it could be a circle, it could be a shaded region, it could be really anything. It's even a single point. Any set of ordered pairs. Keep in mind that this one is what we call a finite relation because it has a limited number of ordered pairs. This one would also be finite, but the rest of these would be infinite or infinite because they have an infinite number of ordered pairs. Kind of the other thing about this is that they're ordered pairs. Pairs kind of imply that we have two coordinates for each of these. We're going to have a first and a second, what you guys have referred to as an x and a y. Before we get into that, I'm going to talk about one-dimensional graphs, or we'll call 1D graph. We have done these before. 1D graphs are number lines. And a number line looks a lot like this. Number lines have an origin, and then they're separated into two different regions. We have the positive region and the negative region. We can space these out however we want. And these tick marks can mean whatever we want, but in essence the right side are positive numbers, the left side are negative numbers, and the tick marks denote whatever markings we want, but really there's a whole everything in between, and that's an important concept to hold, that it represents an infinite number of numbers. So I'm not going to label these right now, there's really no point in labeling them, but this is the real number line. The thing about the real number line with 1D graphs is that they use only one variable. Like when you're solving for only one variable. And most of the time that variable is an x. Let's contrast that now with 2D graph. A 2D graph is where I take that number line and I actually create a second number line and put it in a different dimension. And that crosses, and that gives us our 2D graph. This is still where we plot x, but now here is a y-axis as well. X-axis, y-axis. We have an origin, and that's at the ordered pair 0, 0. This 2D graph has a more common name. It's called the Cartesian Grid, or we can call it a coordinate axis. I'll have a line graph tool for this that will make it a little bit easier to do. We can call it, instead of the real numbers, it's actually the real numbers squared, what higher mathematicians called R2. And we look at this in sort of a counterclockwise way. In this order, we label the regions. Region 1, in region 1, or quadrant 1, x is positive and y is positive. Then in quadrant 2, x is negative and y is positive. In quadrant 3, x is negative, y is negative. And in quadrant 4, x is positive, but y is negative. We also have different regions. If I were to ask kind of how many regions the graph is divided into, we do have 4 quadrants. It's kind of important to know. Quadrant 1, or quadrant 4, quadrant 2, here's quadrant 1, here's quadrant 3. But I also have a positive x, a negative x, a positive y, and a negative y, and then we have right in here the origin. That's actually 9 different regions. That kind of separates this grid out. So you don't have to shade those if you don't want to. I'm just kind of creating this thing here. Every single point on the grid has two coordinates to it. We have an x and a y, and these have different names as well. The x is called, we can call it the x coordinate. We can call it an element, meaning a piece of, or an element of the domain. And we can call it the abscissa. And then the y has some names too. Y coordinate. I can call it an element of the range, or a piece of the range. And I can call it the ordinate. Those last two are new, abscissa and ordinate, and there's some older terms for this, but I did want you to see them. So sometimes we can describe these different shapes up here by listing them, but sometimes we can describe them with equations. A relation can be defined by an equation. For instance, here is a relation that is defined by an equation. It's a relation called x minus y equals 4, and it's made up of all the ordered pairs where x minus y is equal to 4. Let's kind of list some ordered pairs. If I put some xy's and start listening, just give me any two ordered pairs that work, like, if I have 0 and negative 4, or 9 minus 5 is 4, or 10 minus 6 is 4, or 22 minus 18 is 4. You get the idea. I'm getting two numbers that when I subtract them become 4. And I could keep that going on and on. I wouldn't even have to do whole numbers. I could do fractions, I could do decimals, I could do irrational numbers, I could do 1.5 minus what is 4. Ooh, that's a little more challenging. 1.5 minus y equals 4. And go ahead and subtract 1.5 from 4, and I would get 2.5. And then y would be negative 2.5. So not always the easiest thing to kind of do, but we can get any ordered pairs that we want to. I could reverse this, and I could ask, is 5, negative 1 a solution to x minus y equals 4? This is still the same problem. That's still the same thing I just had up there. And if 5, negative 1 is a solution, that means that when I would substitute 5, negative 1 in, and I would do 5 minus a negative 1, I would ask, does that equal 4? So 5 minus a negative 1 is the same as 5 plus 1, which does not equal 4. So no, it is not a solution. That's a yes or no question that you prove by substitution. The second example we're going to do is we're going to take an equation, 2x minus 4y equals 5, and I'm going to solve it for y. Well, if I want to do that, I'm going to subtract 2x from both sides and get negative 4y is equal to 5 minus 2x, and then divide by a negative 4, and I get y is equal to 5 minus 2x over negative 4. And if I multiply the numerator and denominators by a negative, I can switch that and make it 2x minus 5 over 4, which is a lot simpler. And then, as a little sub-problem, what I can do is say, well, what do I get when x is equal to 10, y is equal to what? And I could say, well, that means that 2 times 10 minus 5 over 4 is 15 over 4. So y would be 15 over 4, and that would mean I'd have an ordered pair of 10 5/4 as one of the possible ordered pairs. I could reverse this and say x is equal to what when y is equal to 0. Well, for that one, I'm going to actually want to go back to the original one because that's probably a little bit easier. You can just substitute there. 2x minus 4 times 0 is equal to 5 and figure out what x is. 2x is equal to 5, x is equal to 5 halves, and I have 5 halves 0 is another ordered pair. Let's kind of separate these out. What if I asked a question like this? 1/2 comma what? Well, same thing, and it's probably easier to use the one we did when we had the y equals. I'll grab this and bring this down. I have y is equal to this, which is equal to 2 times 1/2 minus 5 over 4, or 1 minus 5 over 4, or negative 1 or negative 4 over 4, or negative 1. So my ordered pair is 1/2 negative 1. I can keep doing this forever, just making up examples. Number 3, if I put down a coordinate axes, and I just say, let's graph some ordered pairs. Let's graph 0, negative 2, negative 3, negative 2, and negative 5, 0. Remember that the first one tells you right or left, and the next one tells you up or down. Basically, right or left is along the x-axis, and up or down is along the y-axis. So 0, negative 2 is right 0 and then down 2. Negative 3, negative 2 is left 3, down 2. Oops. And then negative 5, 0 is 1, 2, 3, 4, 5 right here. That should all be review for you. As a last one, let's kind of label these down a little bit. I'm going to put a ton of points down. 1, 3, 3, negative 4 thirds, 5, 0, negative 5, 1, 0, negative 5, 17, 1/2, 0, 0, negative 1, 1, and 0, 184. And I want you to tell me which of the regions these are in. And I'll give you your options. Just like up above, we're going to have 9 different regions that you can say. You can say quadrant 1, quadrant 2, quadrant 3, quadrant 4. You can say positive x-axis, negative x-axis, positive y-axis, and negative y-axis. So, let's go to 1, 3. Right 1, up 3, that would be, you should be able to do this without looking, so I'll let you pause this, answer this, and come back, and I'll just kind of go through these now. Quadrant 1, this is right and down, so that's quadrant 4. That's right and nothing, so that's positive x. This is left and up, so that's quadrant 2. Left to right down, or left to right 0, but down 5, so that's negative y. Right and up is quadrant 1. That is the origin. That's the only one I didn't mark here. I should have. Origin's the 9th region. Left and up is quadrant 2. And nothing, and then up is positive y. So just some examples of where you can find things. We're going to end there. This is going to be mostly a review thing, but that's it.